Hey everyone, and welcome to Chapter 4, Section 4.1. In this section, we're going to be talking about solving systems of equations, which basically means that we're going to be solving more than one equation simultaneously. So a collection of two or more linear equations is called a system of linear equations. So this is one way of writing that. If you have We have two equations here. They're both linear. 2x plus y equals 7, and x minus 2y equals 6. And so by a solution to a system of linear equations in two variables, we mean an ordered pair xy that is a solution to all of the equations in the system. That is to say, whenever I take the solution and I take the x value and y value and plug them into either of the equations, I should still get a true statement. So again, kind of abstract. Let's jump into an example, and hopefully it'll be a little bit more clear. So given a system of equations, you can check whether some points are solutions or not. So that's what we're going to do. First up, we have the point 1, 3, and to check if that is a solution, I'm going to take the values I have for x and y, and I'm going to substitute them into both equations. And so if we take the point and plug it into the first equation, we get 0 equals 0, which means that 1, negative 3 is a solution to the first equation. Now we want to take the x and y values and substitute them into the second equation. And I get 1 plus negative 6 equals negative 5, which is of course true. So that means that 1, negative 3 is a solution to the second equation as well, which means that yes, this point is a solution to the system. Let's check the other one. All right, so for the first one, I get 0 equals 0. So 0, 0 is a solution to the first equation. Let's check out the second one. And for the second equation, we see that we get 0 equals negative 5. And the point has to be a solution for both equations. You have to check both of them. So 0, 0 is not a solution to the system. So all told, we're going to look at 3 different methods for solving these systems of equations. I'm going to do one right now, and then the other 2 will be in subsequent videos. So first method is graphing. The very first step is to take these linear equations that we have and graph all of the lines on the same coordinate axes. Then you look at the picture and figure out, okay, do these lines intersect? Do they not intersect? Or are they completely on top of each other? So you want to identify the solutions or lack thereof. If all the lines intersect at the same point, you want to identify what that point is. That is your solution. Just that one point. If you run into a case where 2 of your lines are parallel, then there can be no solution because those 2 lines never overlap. Or if it happens that the lines are the same, then the system actually has an infinite number of solutions. So let's look at an example. So here's a system we want to solve by graphing. It's the previous system that we talked about, that we checked solutions for. So I have to graph each of these guys. So we can graph these equations any way that we choose. Since I'm seeing that y does not have a coefficient other than 1, I'm going to change it into slope-intercept form. So I'm just going to take this equation and subtract 3x from both sides, and I get y equals negative 3x. So this means that I have a y-intercept of 0 and a slope of negative 3. So a y-intercept of 0 means my line goes through this point, and a slope of negative 3, remember there's a secret 1 here, a slope of negative 3 means for every 1 space to the right I move, I have to go down 3 spaces. And my line goes through those 2 points. Alright, so there's one of our lines. I'm going to do the other one. Let's do this one with intercepts. Remember that the x-intercept is when y is equal to 0. So I'd have x plus 2 times 0. Or I'd have x equals negative 5. Alright, so the x-intercept is negative 5. And the y-intercept means I plug 0 in for x. Or that y is equal to negative 5 halves. So negative 5 halves is 2.5. That would put that second point right there. Then I want to draw my line. Okay, and let's see. So the 2 lines intersect at this point here, which is the point 1, negative 3. And that means my solution is 1, negative 3. Okay, another example. So the first line, I know b is negative 3, and m is equal to 1 over 2. So here's b, and then for every 2 spaces right that I go 1 space upward. For the second one, I'm going to do the x and y intercepts again. So the x-intercept is when y is equal to 0. So x equals 4 is my x-intercept. Okay, cool. And how about my y-intercept? So I plug in 0 for x and I get negative 2y is equal to 4. Or y is equal to negative 2. Cool, 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 cool. Okay, then I just graph now remember, I'm looking for where these lines intersect, but these guys are parallel. So actually, since they don't intersect, all right, one more example, ought to do the trick. You're going to get really good at graphing if you do a lot of this. Maybe if you work really hard, you might be as good as me someday. So the first line's y-intercept is -3. The slope is 2, so I go 1 step to the right and then 2 steps up. And draw. Again, you can graph these by any method that you like, but I'm gonna go with the intercepts again. So x is 9 over 6, or 3/2. So that's 1.5 for the x-intercept. And the y-intercept is -3. All right, so my two graphs are completely on top of each other. And this tells me that my two equations really are representing the same line. Automatically, if you have an ordered pair that satisfies one equation, it satisfies the second one, since there's infinitely many points on one line. Many solutions. And that kind of covers 3 possibilities that you could have. So let's recap. There's this first possibility where the two lines intersect at one point, this possibility where the two lines are parallel, and this possibility where the two lines are completely on top of each other. So these are called the intersecting, parallel, and coincident cases, respectively. In the intersecting case, we have exactly one solution. It's that point of intersection. This is said to be a consistent system of equations. The system has at least one solution. Here, it has exactly one. And it's also what we call independent, and that means one equation is not some combination of the others. Contrast that with the parallel case, where we have no solutions, so that means it is an inconsistent system. It's still independent though, so if you're the blue line, you can't, say, multiply by a constant and get to the red line. They're still very distinct. And for the coincident case, we have infinitely many solutions because all of the points on the line are solutions. It's consistent because it has at least one, but it is dependent because one of the equations is just a modification of the other. They're really the same line. And that about wraps it up for our intro to systems of equations. In the next video, we're going to look at a different method for solving them.